It's a great pleasure to be introducing my Columbia colleague, Lorenzo Sironi. Lorenzo did his PhD in Princeton, working with Anatoly Spitkovsky, and then he got a prestigious postdoctoral fellowship at Harvard. And after that, he joined Columbia in 2016 as a faculty. Lorenzo did some pioneering work in numerical high energy astrophysics. In particular, he has worked on shocks, acceleration of particles and shocks in reconnection, which he is going to talk about today, and also more recently in turbulence. He has applied his work to numerous astrophysical objects, fast radio bursts, coronae of accretion disks, pulsar nebulae, accretion flows around supermassive black holes. So welcome, Lorenzo. Please tell us something interesting about reconnection.
Okay, thank you, Yuri. Very quick preamble. I will try to make this presentation about reconnection and its astrophysical implications as fundamental as possible and as accessible as possible, but especially for students, if there is jargon that I'm not defining, just stop me. I will not be keeping track of the chat, so I ask Yuri to keep track of the chat or just interrupt me and ask for clarifications as we go along. Okay, so what I would like to present today is some recent work that we have been doing, roughly speaking, in the last couple of years in, first of all, understanding the fundamental physics of particle acceleration in reconnection, especially the relativistic regime, which I will be defining, and then understand how this can be used to interpret some puzzling astrophysical observations. So first I need to define relativistic reconnection, and in particular the regime of relativistic plasmas. And by that, I mean that this parameter, which will appear over and over in my presentation, the so-called magnetization, is larger than unity. That's a peculiarity of astrophysical systems. This magnetization, or sigma, quantifies, roughly speaking, within a factor of 2, the ratio of the magnetic energy density to the particle rest mass energy density. So if you're dumping this magnetic energy into particle energy, your particle will acquire a characteristic Lorentz factor of order sigma. So they will immediately become ultrarelativistic if sigma is much larger than unity. And really, this is not a regime that we can currently probe in the laboratory. So astrophysical systems, as exciting as they are, they also provide a useful tool to understand the basic plasma physics of reconnection in a regime that is not accessible for laboratory experiments as of today. Okay, so this is the regime of relativistic plasmas. What is reconnection in the relativistic regime? So it's a process of annihilation of magnetic fields. The blue and the red are magnetic field lines in the regime in which they carry an energy density larger than the rest mass energy density of the plasma. This is the relativistic part of the reconnection process. Reconnection is widely studied in the lab, in the solar wind, solar environment, solar corona, and in astrophysics, where the astrophysical uniqueness is indeed the fact that this magnetization parameter can be much larger than unity. The fact that these field lines are moving with respect towards this central region with some velocity implies that there is an electric field from just V cross B, and this electric field for reconnection is of order 10% of the magnetic field. So whenever you have an electric field, you have the potential for accelerating particles, and that's what the emphasis of this presentation, of this lecture, will be about. How can reconnection explain the requirement of particle acceleration in astrophysics, and how does reconnection accelerate particles? So the first part of my talk would be on sort of like a 101 introduction to the physics of particle acceleration in relativistic reconnection, especially with advances and updates that have emerged in the last, I would say, 6 months. In order to address this point, we need to rely on large-scale numerical simulations, especially the ones performed with the so-called particle-in-cell technique, which is a very fundamental plasma physics method of capturing the interplay of charged particles and electromagnetic fields. And basically what you're doing is to solve for the particle motions in the grid. According to the Lorentz force, the moving charged particles are creating a current. The current is then used to solve for Maxwell's equation, through Maxwell's equations for the electric and the magnetic fields, which are used in the Lorentz force to push the particles around. So the loop continues and you have a constant self-consistent interplay between the particles, the charged particles and the electromagnetic fields. We're capturing the correct plasma physics on the so-called plasma scales. The typical length scale is the so-called plasma skin depth. The typical time scale is the inverse of the plasma frequency. If you plug in a typical density, astrophysical density of 1 particles per cc, these length scales and time scales are actually quite small. So the main effort in performing the simulations is to extrapolate the results to astrophysical scales. That's the challenge. With the simulations, however, we can answer basic fundamental questions of the physics of magnetic reconnection. So let me just start with an example. This is a representative simulation, peak simulation, particle cell simulation of reconnection in a regime in which you have 10 times more magnetic energy than the rest mass energy of the plasma. This is the direction of the two opposite polarity, opposite direction magnetic fields. And you see as the system evolves that this is a very dynamical system. It creates structures, which we call magnetic islands or plasmoids in the middle of the domain. These structures can actually merge with each other and grow bigger and bigger. This simulation is performed with outflow boundary conditions. So there is a net motion to the left and to the right, which is bringing those structures away from the simulation domain. The fundamental question, though, and the reason for why we're doing particle in cell simulations is to understand the physics of particle acceleration. And what we want to do is to understand how this very dynamic structure can actually translate into properties of accelerated particles. So this is how I will be spending the next 15 minutes. And let me just start with a preamble that any accelerator should actually be responding, should actually be addressing 3 fundamental questions or 3 fundamental stages. This is actually a simulation done, a hybrid simulation done for non-relativistic shocks, but it very nicely illustrates the 3 fundamental stages of any accelerator. The first one is the so-called injection. Injection decides how many particles are not part of the dominant Maxwellian distribution, but they are actually pushed to higher energies. The second question is the formation of a power law tail. And what are the properties of the power law tail? What's the so-called slope of the power law tail? And finally, how far you can push your accelerated particles, or equivalently the maximum energy, the cutoff, the spectral cutoff of the spectrum. These are 3 separate questions, and these are 3 questions that we can also ask for reconnection in the relativistic regime, and that I will be describing in the next few slides. So let's start with injection. What controls the energy or the fraction of particles that can participate in further acceleration? The other way to phrase it is reconnection is bringing particles into the midplane, into the region where the field is being dissipated, and those particles are starting as cold. And potentially they can be promoted by dissipation of the magnetic energy up to a Lorentz factor of order sigma, sigma divided by 2, or even slightly above it. So how does this happen? And the answer is that a particle, in order to be injected, needs to be in the right place at the right time. In the context of reconnection, this means interacting with the so-called non-ideal fields. Ideal magnetohydrodynamic prescribes that the electric field can be written as minus V over C, the bulk velocity of the flow, crossed with the magnetic field. So non-ideality is whenever this condition is not satisfied, where the electric field is not equal to V over C cross B. And there can be 2 realizations of this. One is the case in which the electric field is larger than the magnetic field. The velocity is always smaller than the speed of light, so E larger than B means non-ideal conditions. This happens for reconnection in the case the so-called guide field. This BG is an additional component of the magnetic field, which is perpendicular to the two alternating fields. So if these are the two alternating fields, the guide field is a component orthogonal to them and uniform. On the other hand, if the guide field is strong compared to the alternating component, larger than 0.1, the non-ideal effects are captured by the so-called E-parallel, meaning the electric field aligned with the magnetic field. I will be focusing on the left case and discuss and show how the condition E larger than B is indeed leading to injection of particles. So I'll do that with a movie. This is a prototypical simulation of reconnection that we started doing almost 10 years ago now. The small yellow dots are particles that are starting at the same distance away from the mid-plane, which is right here. And in particular, I am emphasizing the yellow, the red, and the orange particle. And for them, in the bottom panel, I have their trajectory in energy space, meaning their evolution of their Lorentz factor as a function of time. The vertical dashed line for the red particle and the orange particle signify locations where the particle, time locations, where the particle for the first time is experiencing E larger than B, meaning non-ideal regions, non-ideal effects. So we can have the movie run, look at the red particle first. The red particle is experiencing non-ideal fields about now, when it first interacts with the reconnection layer. So it found itself in a location where the electric field was larger than the magnetic field. This is the perfect situation to be energized. You don't care about the magnetic field, you're just boosted along the electric field. And in fact, this particle energy increases immediately to Lorentz factors of order 30 in a very rapid way. And then the particle is really not doing much more. Now the orange particle comes and it's doing the injection, it's experiencing E larger than B. Now, when these two large structures, these plasmoids or magnetic islands, merge with each other. So this is again accompanied by the formation of a reconnection layer in between with E larger than B regions. And by interacting with one of those regions, the orange particle can be promoted to high energy. Again, a rapid process over time. On the other hand, the yellow particle never really went through any E larger than B episode. And so its energy stays relatively small with the Lorentz factors of order unity. So this is the first conclusion that we have about the fundamental physics of relativistic reconnection. Promotion to Lorentz factors of order sigma, which can be ultra-relativistic, happens if the particles are finding themselves at some point in their life in regions where the electric field is larger than the magnetic field, or non-ideal regions more in a broader sense. What is the resulting particle spectrum? We need particle spectra and spectral slope to model astrophysical sources of non-thermal radiation. So in this injection stage, the power law can be as hard as 1. And by that, I mean the number of particles differentially in Lorentz factor can scale like the Lorentz factor to the -1 power, which is a very hard slope, but it does not extend to infinity. The injection stage is only able to accelerate particles up to a few times sigma, sigma demagnetization, which I'm also defining here once more. And now this conclusion is well established. Various groups, 2D, 3D, electron-positron, electron-proton, electron-positron-proton plasmas. So it seems to be a robust conclusion. The slope is harder, as this plot shows, for higher magnetization. Here we're plotting the number of particles as a function of their Lorentz factor. And the slope is indeed indicating that the higher the magnetization, look at sigma equal 50, for example, the harder the spectrum becomes. So the spectrum is not universal. It's sensitive to magnetization in the direction of harder for higher magnetizations. Injection,
Lorenzo, sorry,
fields are essential. Yes, go ahead, Pasquale.
Lorenzo, just a quick question. In the simulation you showed earlier, what's the size of the Larmor radius for that particle compared with the structure that I see here? What's the Larmor radius of the particle with Lorentz factor 30? Yeah,
so it's about I would say the dominant energy, which you say for 3 sigma is 30, if that's what you have in mind. The particles that are accelerated up to sigma have a Larmor radius that is slightly larger than the thickness of the layer. Thickness of the layer meaning in the thinnest regions. The particles, of course, is starting cold, so it's very strongly magnetized. It's being brought into the layer. And then as a result of this impulsive episode, which brings them up maybe to 3 sigma, 5 sigma, if you're generous, it gets to a Larmor radius that is comparable, larger than the thickness of the layer, comparable to the size of the smallest plasmoids in the layer.
Okay, thank you.
Then you need to think about something that will bring you to higher energies, okay? And I'm gonna get there.
Right.
Yes.
Yeah.
Lorenzo, there are a couple of comments on chat. First by Carl Meinem saying that efficiency must be low because of the sparse topology of regions where E is greater than B.
Great question. So ask me the question later again, because I do have a backup slide that I can show this more quantitatively. But if you do pay attention to this number, this is exactly quantifying your question. These are the number of particles that at some point in their life, as time progresses, are experiencing E larger than B fields. And it's about 20% of the initial particles. So it's not negligible. And it is misleading to consider the filling fraction of plasmoids over the volume. What really matters is the occupation fraction, sorry, not the plasmoid. What these regions of E larger than B, what matters is not their occupation fraction in the volume, but what matters is their occupation fraction along this line. Because all the particles are brought to this line. So then it matters whether a particle is finding itself in a region E larger than B or not, along this line, not in the volume. And the E larger than B regions along that line account for about half of this 20% that I'm quoting here. The reason for why it's half and it's not 20%, so it's 10% and not 20%, is because equal number of particles are injected when intersecting the layer at the initial time and during the plasmoid merger phase. So it's about 10% at the initial phase, 10% at later stages. And in fact, if this movie will be running again, you see the first interaction of the particles with the layer brings them up to about 10%. Maybe it will get to 10%. And then it's the second 10% is during the merger of the two big plasmoids.
So there are two other questions. I don't know if you want to take them now.
Let's take them. I am flexible in the sense that I have a second part of my presentation that we can also not talk about. Questions are very welcome.
So I don't know, Eamon and Paolo, do you want to ask your questions with your voices?
Yeah, sure. Thank you. My question was, like, if I see this simulation, what's the difference in the trajectory of, let's say, the red boosted particle versus the yellow particle, which is not getting this boost? The difference in sort of the global trajectory?
So before they interact with the layer, there is no difference statistically. What matters is when they interact with the layer, they happen to be in E larger than B regions or not, if you're just comparing the yellow and the red, for example. And that is the critical difference. Now, these E larger than B regions are in between plasmoids. So they're very small in some sense, each of them. So it's hard to see them here. But that's what determines the difference, right? Is it if you're ending up as you move towards the layer within an E larger than B region or not? That's the difference. And the trajectory after that is actually very affected by this initial stage because the particles that end up with gamma of order 1 are very strongly magnetized. The particle that end up with a gamma of 100, then they're not as strongly magnetized and they can actually experience other acceleration mechanisms that otherwise, if they were to be strongly magnetized, they would not be able to enjoy.
Okay, thank you.
Paolo?
Yeah, and my question was, why do you get a power law in the injection stage? Because it looks like you're getting discrete kicks, and a power law is like Fermi, you have something stochastic. So is this reflective spectrum of turbulence?
Yeah, so there has been a very nice paper by Dimitrius Densky last year, which is phrased as the power law of particles accelerated in reconnection. But I think the better way to phrase it is really the power law of particles accelerated in the injection phase of reconnection. And it can ultimately, the ultimate story is that the power law index is set by the interaction with these E larger than B regions. Mm-hmm. And the electric field is setting the accelerating power. And then the escape from the accelerator is how fast you're advected away from the acceleration region by the reconnected magnetic fields. And this balance is sigma dependent, actually dependent on the Alfvén speed ultimately, because that's controlling the speed of the field lines that are advected away. And this may be a justification for why the power law index is harder for higher sigma. So I will refer you to that paper, Uzdensky 2020-2021.
Okay, thanks.
Okay, injection. Now, maximum energy. This is where things start to be even more exciting. So for a long time, we were actually stuck as the particles were by thinking that the highest energy particles would actually be confined in plasmoids, in these magnetic structures that reconnection self-consistently generates. But then we started looking at 3D simulations with some detail, and we found that lucky particles can escape from plasmoids and wiggle freely from the two sides, back and forth between the two sides of the layer. So this is one particle trajectory in 3D. Its spatial trajectory is projected in the XY plane. That's the plane of the alternating fields. And then the ZY plane is the plane perpendicular to the alternating fields. And you see that especially at late times, now the movie will be running again, you have the particle experiencing this back and forth motion. It's kind of stuck in the plasmoid still now, and then it will break free. And when it breaks free, it will start surfing essentially the reconnection layer with orbit that involves both sides of the layer. And when it does so, the particle energy increases linearly with time. And the particle is accelerated by the fact that in the region away from plasmoids, up and down in these plots, you have the electric field, which I discussed at the very beginning, that just V cross B. It's an ideal field now. Non-ideal effects are not relevant for this further acceleration stage. This field is about 0.1 of the magnetic field, and the acceleration is linear with time, which does not happen in 2D, but it's an old story now. So if you plug in basic numbers, you can get, for example, that this fast acceleration allows to get to ultra high energy cosmic rays for representative parameters of blazar jets. So reconnection is fast, and the highest energy particles are actually experiencing this quasi-oscillatory motion between the two sides of the reconnection layer. So this insight, this novel result, allows us now to build a theory for the power law formation beyond the injection stage. So now we're talking about forming a power law beyond the injection stage, which itself creates a power law. So we're starting with something very basic. This is just the sort of like most fundamental equation for particle acceleration in astrophysics. It describes how the particle distribution F, number of particles differential in energy, depends on the acceleration time and the escape time from the accelerator. We're assuming that all the particles are injected at 3 sigma. I already discussed the injection physics. And the result is that if the acceleration time and the escape time depend linearly on the Lorentz factor, the solution is a power law with an index corresponding to the ratio of the two time scales. There is no physics here. This will hold regardless of the acceleration and escape time, but the key is indeed, what are these two times? What's the acceleration time? What's the escape time? And that's what I will try to argue in the next few slides. So let's look again at this 3D novel particle tracks, especially during the phase in which they can break free from plasmoids and experience the large-scale electric field by doing this surfing between the two sides of the layer. So the minimal model that we propose is the following, where this is a ZY cut. So it's the same as the right top panel. The particles are accelerated only when they are in the region away from plasmoids, which we call upstream. And they're accelerated with nearly the maximal rate Here, eta rec is 0.1. That's the ratio of the electric field to the magnetic field. And they, when they are trapped in plasmoids, they are actually not accelerated. This is consistent with our simulation results. Acceleration in plasmoids is much slower than the acceleration by these large-scale electric fields. So at 0th order, we can neglect it. So for these particles, which are happily surfing between the two sides of the layer, the escape from the accelerator is when they get trapped in a plasmoid. Okay, so that's the key part. The active acceleration is the region which is black in this cartoon. And the blue regions, the plasmoids, are the graveyards of accelerated particles in 3D. Particles are not getting efficiently accelerated there. So again, when they get trapped in plasmoids, they're effectively escaping the accelerator. Okay, so now we have a model. We can measure directly from about 1 million particles in our simulations, the acceleration time and how it scales with the particle Lorentz factor, while in the active acceleration region, the escape time, which, as I said, corresponds to the time when the particles are trapped in a plasmoid, because that will be the end of their acceleration. We measure both, and they both scale linearly with gamma, which is good for what I said earlier. And their coefficients are not very different. They're about, this coefficient is about 30 in both cases. So we have now a direct probe of which power law is appropriate for the particles. And the power law index is -1. However, these particles are the particles that at any given time are freely accelerating by doing this wiggly motions from the two sides of the layer. That's why I'm calling them free particles. They're the particles that are not trapped in plasmoids. That's their expected distribution. We can measure it from our simulation. Here, the spectrum is renormalized by an extra factor of gamma -1. So for a slope of gamma -1, you would expect this to be flat. This is the red line, the spectrum of the free particles, and it's indeed flat. So we have proven that free particles in reconnection have a slope of gamma to -1, consistent with the argument of trapping and acceleration times. But we can go one step further. We can ask, okay, these particles at some point will get trapped. What's the spectrum of the particles in the whole reconnection region, which includes the free particles and the trapped particles? So the argument then is to say the rate at which the free particles are getting engulfed, trapped inside a plasmoid, must be equal to the rate of the trapped particles advecting out of the system for steady state. Simulations have outflow boundary conditions, so this statement about particles being advecting out of the system is meaningful. So under this assumption, what you find is that the distribution of free particles should just be the trapped particles, should just be the distribution of free particles times the ratio of the advection time out of the system divided by the escape time, meaning the time that the free particles end their acceleration by being trapped in a plasmoid. Advection time is gamma independent. The escape time, as I just proved, depends with gamma linearly. So you're effectively steepening the slope with respect to the distribution of free particles by an extra factor of gamma, gamma to the -2. That's the distribution of particles beyond injection from the reconnection layer. And what we find is that, remarkably, this is sigma independent. We have tried for high sigma, sigma 3, 10, 30. The slope always seems to be -2, so corresponding to a P of 2 for the energy range gamma larger than 3 sigma, which corresponds to beyond the injection stage. So final results, you can take pictures now. Reconnection actually gives a broken power law with the break happening at a few sigma, 3, 5. Below the break, the distribution is sigma dependent, and it can be as hard as P of 1. So slope of -1. Beyond the injection stage, much less dependent on sigma, nearly independent as you go to sufficiently high sigma, and the asymptotic slope is P of 2. Now, just a note on this 3 sigma, if you're interested in ion acceleration, sigma is the magnetization of the flow. If you're interested in electron acceleration, this sigma should actually be replaced by the electron magnetization, the magnetic energy per electron, or the magnetic energy density normalized to the electron rest mass, which is a factor of 2000 larger than the ion sigma. So if you have an outflow with a sigma of 1, then the electron sigma is 2000, so the break is already at the gamma of order 2000. This will terminate my sort of like fundamentals of relativistic reconnection particle acceleration. So if there are questions on the origin of the power law, I'm happy to take them now. Otherwise, I'll move on to the astrophysical applications. Okay, so I want to focus on a couple of systems.
Sorry, Lorenzo, there is one question from Udi in the chat. What about particles that escape more than once?
Yeah, so it does happen, but it doesn't happen very often. You mean particles that are trapped in plasmoid and then they escape again from plasmoids and they're trapped again? This is relatively unlikely. What we find is that most of the particles are going through one free acceleration stage. So the theory is really built for those particles neglecting the injection, if you want. You would call this injection at higher gamma. And instead, we model all of the injection is happening at 3 sigma right after the injection stage.
Surprising. It's a bit surprising because it's harder to trap more energetic particles. So you have a particle which is already went through one acceleration. It is much more energetic than all the rest of the particles. And then you say that the probability that this particle will escape again is lower than the probability that other particles will escape.
I'm saying that this particle will actually never be trapped. So the particle trapping is a state.
So if it's not trapped again, then it continues to accelerate infinitely?
Indefinitely, yeah, that's a big word. So the plasmoids are actually acting to scatter the particles towards the outflow direction. So even though they are, so I guess the escape can happen always in the direction periodic, which is the z direction, which we are not really capturing escape along that direction. That should be relevant astrophysically, but it's not part of the simulations. As the particles are interacting with plasmoids, they may still be free, meaning not completely trapped, but they will get a kick from the plasmoids towards the direction of the outflow, the same direction where the plasmoids are moving. So at that point, those particles will be lost from the system. Still in the free stage, so they're not engulfed by the plasmoid, but they're lost from the system. So there is an escape of free particles as well, remaining free from advection out. Now, the point about trapping, I would phrase it this way. A particle that is trapped is because it's encountering a plasmoid that is significantly larger than its Larmor radius. Otherwise, it will not get trapped. And in fact, we do see this. The reason for why the escape time is larger for higher energy particles is just that the structures that could trap those particles are fewer and fewer in the system. But when it gets trapped, this particle is in the condition of not actually getting free again very easily.
And so you have 3 more questions. One from Frank.
Thank you.
I'm happy to continue this over the discussion, Udi, if this is not clear.
Thanks.
Go ahead.
So Frank Rieger is asking, what about radiative losses?
Yeah, so I'll talk a little bit about them later. I would say at 0th order, if the radiative losses are very strong, this second power law will never appear. It's not very different than the usual argument of comparing the acceleration time to the cooling time. Okay, so if your cooling time is faster than the acceleration time, which has a simple expression here, it's just the gyro time divided by the reconnection rate. So about 10 times the gyro time, 30 times, that's what we measure. If this time is longer than the cooling time, then those particles will not break free and will not experience this acceleration physics. Electrons will seriously suffer from this. ions, if we're interested about ultra-high energy ions, this is what they're expected to do within a reconnection scenario, because they will not, unless you are in very dense environments with hadronic losses and so on. But ions will participate in this.
We have a question from Paolo.
Yeah, I was wondering, so when you have escape, there's a reconnection picture from Francis Drake, I guess, where they have Fermi acceleration off islands in the outflow. So are you sure your escaping particles don't bounce off other things and you're just seeing the box limits of your box and a lot more could be happening past? And how do you, is your system significantly different because it's highly magnetized and his isn't? Like, what's the difference in the pictures?
Yeah, so I think that the non-relativistic connection is yet to be, I would say, fully characterized. My feeling is that one needs to be clarifying whether it's a difference between non-relativistic versus relativistic conditions, or is a difference between 2D and 3D, because we have been for several years characterizing acceleration processes in 2D, and then only in the last couple of years realized that what we thought were the dominant agents of acceleration, which in 2D happens within plasmoids, actually leads to much slower acceleration rates than the 3D free evolution. And I should also say that recent non-relativistic reconnection simulations have shown that particles can, maybe not as in the extreme case that I'm presenting here, in which the particles are even sent back upstream, but they can experience multiple plasmoids. They can move from one plasmoid to the other, which in the original picture by Drake, which was a 2D picture, was not happening because the particles were strongly magnetized and sort of like tied to the plasmoid that they just happened to be in. There's much more to say, but I'll stop.
Yep. Thanks. Yeah.
Felix, you had a question?
Lorenzo, about the solution gamma minus ratio of the acceleration to the confinement time. So it's a bit, looks like it should not be very stable solution, right? I mean, how it could be just one or two, it could be any number. I mean, large uncertainties there could be, because how you get just exactly one or two or whatever. Moreover, there could be different energy dependencies for confinement time and escape time. And then in that case, you don't have power law at all.
Yes, so I absolutely...
Although that is not important, actually, power law, I don't think it's important issue to have a power law, but just this solution, it looks like a bit mathematically should not be stable solution, right? Or
so I think that, I mean, that has the limitation of what I wrote, of the statement about the two timescales depending linearly with time. We try to measure this directly from the simulations. So that's what I was trying to, argue here. These lines have linear slopes. It is the best fit. I would say the best fit, if you're keeping the slope free, is between 0.9 and 1.1. I honestly cannot say whether it's 1.1 versus 1, the slope, but it's consistent with having a linear scaling. For the acceleration time, it's obvious, I would say, within this model that it should have a linear scaling, because the acceleration rate is a constant. It's this one. It's just acceleration by the electric field. So the linear dependence with gamma is obvious. The escape time or trapping time, whether it's actually scaling linearly with gamma, I have some ideas for why this should be, but this is intrinsically related to the plasmoid structures, and that's a nonlinear. These are nonlinear structures merging with each other. So having a fundamental understanding of why this should be gamma scaling with gamma, I think we're not there yet. Now, why this is why the two timescales are equal? I think that's a very it's a very interesting question, and I'm still scratching my head. I mean, these are stuff that we have been doing really in the last couple of months. So I'm very excited about talking about it, but I'm sure this is also a great environment for having discussion about it. So I think one potential indication is the fact that if you're just taking the 2D reconnection rate, two-dimensional reconnection rate, and then you're computing the acceleration time corresponding to that, then you find acceleration time smaller than the measured escape time. So this will lead to a slope for the overall particle distribution. So the one that is gamma to the -2 here, this will lead to harder slopes. Now, this is energy diverging, of course. So you cannot push this to higher and higher energies other than by changing the slope. So I think possibly, but this is just an idea at the moment, possibly the pressure of these accelerated particles is back reacting on the reconnection physics, such that to lower the reconnection rate and steepen the slope. But I'm saying this, and I'm also saying this with a lot of caveats, because I think this has to be carefully tested.
Okay,
Frank, you had something else you wanted to ask. Frank Rieger?
Can you hear me? Lorenzo, this is super interesting. Just for me to understand, this is for a connection of quasi anti-parallel fields.
Yeah.
So say if a linking or a guide field, it would change the escape, and I mean, would complicate things quite a bit, right?
Yeah, I don't know. Yeah, I don't know. I think there are definitely two competing effects. The guide field will actually encourage particles to move along the direction of the guide field, which is the direction by which the particles are escaping from plasmoids. So that might actually help in having more particles getting free. On the other hand, it's also known that with a strong guide field, the plasmoids are more elongated along the direction of the guide field. So particles will actually have a harder path to cover before escaping along that direction. I don't know. It's a good question. I don't know. Okay, so let's get to the astro implications. So most likely we'll not get to black hole coronae, but I would like to spend some words on how reconnection can explain the multi-wavelength, multi-timescale emission from blazars. And then maybe in the discussion we can talk, oh wow, it's 9:44. We can talk about how radiative reconnection can explain the hard state of accreting black holes in X-ray binaries. So what about blazar jets? What we're looking really is reconnection happening in the core of the jet, where sigma is most likely 110, definitely larger than unity. And I don't really need to introduce blazar jets for this audience. Jets moving towards the observer, characterized by broadband spectrum, synchron bump at low energies, inverse Compton bump at high energies. Magnetic fields are definitely there, both because the engine most likely is threaded with magnetic fields and launching the jet as point influx dominated outflows, and because of direct evidence of radio and optical polarization, infrared and optical polarization. So the few requirements that we ask for any model of blazar emissions, it needs to be producing non-thermal particles, ideally powerless, but I agree with Felix, not necessarily. Some of them need to have a hard slope. This is already, I would say, I already convinced you that reconnection can actually do it. The injection part can be harder than 2. The post-injection part, I'm arguing, is sigma independent and P equal to 2. The other 2 points I would like to emphasize, because they're kind of puzzling for blazar observations, is the presence of very large sweeps in the polarization angle. So this is in the optical band, the angle of the polarized emission, most likely produced by, I mean, definitely produced by synchron emission. In this extreme case, the variation of the polarization angle is 720 degrees. Most of the other cases are more than 90 degrees or a little bit more, but we need to find an explanation for this. The other point that I will focus the attention on is the so-called orphan flares in the gamma ray band, which are very bright in the gamma rays, but don't seem to have a significant synchrotron counterpart, low energy synchrotron counterpart. So inverse Compton is very bright during those flaring episodes, but synchrotron doesn't seem to be. And I will really not have time to discuss the fast time variability, but you're welcome to ask me questions about that. So polarization rotations. This is work done with David Hosking. And let me remind you the sort of like prototypical reconnection layer with the plasmoids, density at the top, magnetic energy, kinetic energy, and these plasmoids are moving left and right. Larger plasmoids are typically moving slower. You see this guy is actually being caught up, being bombarded from the back by a bunch of other smaller plasmoids, as you can see in this case as well. So there are velocity variations for different plasmoids, and typically large ones move slower and are bombarded from the back by smaller plasmoids. So let's assume now that we just know about a plasmoid right here, and we are somehow assuming that you have an emission front sweeping from the left to the right, and the observer is sitting to the right. So the orange ellipse is the emission front. When the emission is here, the observer is seeing a polarization angle, seeing the top directed magnetic field, polarization angle, let's say of 180 degrees. Later on, the emission front is in the middle of the plasmoid. In this case, 90 degrees. There is a component here that I'm not drawing of magnetic field sticking out of the page. So this is what gives the polarization angle in this intermediate case, where the rest of the magnetic field, the in-plane magnetic field, is along the line of sight. So you're not sensitive to that for the polarized emission. And finally, when the emission front is on the other side, it's the opposite to where it started from. So let's say 0 degrees. So if you have this emission front sweeping through the plasmoid, then you would expect to have a sweep in the polarization angle of order 180 degrees at most. Does it happen? And what's the emission front? So we perform big simulations of reconnection with added synchrotron cooling because this is emission in the optical band, so that's controlled by synchrotron. The main point that I want to emphasize is that we have a cooling Lorentz factor, so a Lorentz factor at which the cooling time is equal to the dynamical time of the system, which is comparable between our simulations and in real blazar jets, about 10 times below gamma sigma, which is the Lorentz factor corresponding to the magnetization sigma. Sigma here is the electron magnetization because we care about electrons, electron emission. So the conspiracy, which is actually the interesting conspiracy, is the fact that the cooling time being 0.1 of the dynamical time at gamma sigma, this is just a consequence of the fact that the cooling time, the cooling Lorentz factor is a factor of 10 below a gamma sigma. This time scale, 0.1 of the dynamical time, is also comparable to the light crossing time of the large plasmoids, which have a size of over 0.1 of the size of the system. So the time it takes for the particles to go around a plasmoid is comparable to the time that it takes them to cool. So cooling time is comparable to the time it takes those particles to cross, moving at the speed of light, one of the large plasmoids. Why is this important? This movie illustrates it. This is our large plasmoid, and what we're showing is synchrotron emissivity. So I'll run the movie a few times. So what you see is that this plasmoid is being bombarded by a plasmoid from the back. And as a result of that, the emission gets very bright. It's happening now again. It's very bright because you have merger, accelerated particles at the interface of the two plasmoids. Those particles will radiate very efficiently. So you have a fresh episode of particle acceleration whenever you have merging plasmoids. You don't need acceleration to very high energies. This is just above the injection stage.
That's the question.
Yeah, let me finish the story. Yes. So you do have these fresh particles being energized here at the merger. So now you see the emission is brighter on one side. So the polarization angle that the observer is sensitive to is this one, the cyan line is the polarization angle as a function of distance here along the reconnection layer. Later on, as the front moves through, now this is the region for which the observer is detecting most of the emission. So that's the polarization angle that it's sensitive to. And then finally, brighter on the other side, the polarization angle now is opposite to the immediate post-merger phase. Okay, I can let the movie run again and take the question.
Okay, so what's it's Amir. Hi. What's the global setup you are envisioning here, like a striped jet? Because you know instabilities will give you turbulence with probably guide field.
Yes. So I think this will likely favor a scenario of a striped jet where you have a relatively ordered reconnection region. This is actually one of the big questions that I would say is up for discussion of what are actually the conditions under which the reconnection layers are being formed. And for example, one could also envision that the acceleration physics that I discussed earlier with these particles being wiggling back and forth across the layer, when the lifetime of those particles becomes of the order of the light crossing time of the system, then if you're embedding this reconnection in a turbulence scenario, you may not even have your reconnection layer there anymore. So I think that's a major question for the higher energy particles. This configuration, I would say, just cares about the two merging plasmoids. Now, you should ask the question of why am I dominated by the merger of two plasmoids and all the other reconnection layers within a turbulent setup don't matter. Beaming may be part of the answer. These plasmoids are actually supposed in this picture to be moving towards the observer. So even the large plasmoid not being ultra-relativistic, some of the Doppler boosting may enhance its emission with respect to other reconnection layers that may not have these favorable orientations.
I mean, actually asking how you go from dynamic range of, let's say, 1,000 to dynamic range of 1 billion or something like this in a realistic system.
So what I think, let me try to phrase your question. So 1,000 meaning that my biggest plasmoids are 1,000 skin depths?
Say scale separation, yeah.
Okay, so what we have shown a few years back is that the plasmoid dynamics actually, at least in 2D, in 3D, we have not really done this yet. The plasmoid dynamics is relatively self-similar, meaning that it's always true that the largest plasmoids are a fixed fraction of the size of the layer. So the numbers that I pick now for connecting this to the observations are, I would say, a layer that is not very different than 30% of the jet cross-section at parsec scales, and which I think is relatively reasonable in order to get the day timescale over which the flip in polarization happens. So this flip, of course, happens on plasma scales. This is one of the biggest plasmoids in the layer being bombarded by sort of like a decent size plasmoid. Scale up, the problem is realistic because self-similarity in the reconnection layer holds as far as we have checked. And actually even non-relativistic MHD simulations are showing that the biggest plasmoids are of order 0.1 of the size of the system. So I think that that's also confirmation, a scale-independent confirmation that you shouldn't really care about the plasma scales for plasmoid size, but more like a phrase it in terms of the fraction of the system size.
Lorenzo, Eloisa Menigoni is asking, for this last simulation, did you use the ABC configuration instead of anti-parallel current sheets?
If I use that?
The ABC configuration instead of anti-parallel current
so
sheets.
all of this is anti-parallel reconnection. The ABC may be helping you in having faster dissipation, even though I would say in the asymptotic stage that the length scales are much larger than your plasma scales. Eventually, you may not be very different than the usual anti-parallel Harry sheet type configuration.
Okay, thanks.
And for if you have in mind the context of a strike jet, as Amir was saying earlier, then I think it is reasonable to indeed start with an anti-parallel case more than like a quasi-equilibrium that relaxes dynamically. Okay, so this is sort of like the outcome. We do have a flare. Top panel in total emission, polarized emission is the red one. The bottom panel is the polarization angle in black. And as you can see, the polarization angle sweeps as the flare happens. This is also observed. There is a relatively accepted correlations between high energy flares in blazar jets and rotations. So what we're showing here is that they may be both coming from plasmoid mergers, and there's emission front sweeping through the plasmoid. So if I still have 5 minutes, I would like to speak very briefly about the orphan gamma ray flares. Yuri?
Please go ahead. Please go ahead,
Okay.
Lorenzo.
So here I want to switch gears a little bit, but by embedding reconnection in a turbulence setup. But in reality, you could take the conclusions that I give and phrase it for a reconnection only scenario as well. What the turbulence is doing to the reconnection is creating these current sheets. This is the overall domain, and you're seeing a zoom in version of it on the right. And you see these plasmoids appearing pretty much everywhere, right here, very dynamic configuration. Differently than most of what I presented so far, this turbulence simulations be initialized with a fluctuating magnetic field over the mean field implies that the reconnection layers that are formed on these large scales have a guide field of order unity. So the component of the magnetic field that is not dissipating is about the same strength as the component that is dissipating. And that's key for what I will be discussing in the context of the orphan flares. Yeah, forget about this. So let me just show one representative particle in turbulence simulations that gives rise to reconnecting layers. What you can see is that this particle is experiencing two stages of acceleration. So the overall domain is here, the zoom in domain is here, the particle is right here, and this is the energy of the particle as a function of time. Let's see if this is right. Yes. So what you can see is that the first kick to particle energy is given now when the particle is on top of a reconnection layer. So within turbulence, the first episode of particle acceleration is provided by interactions with reconnection layers. And then what happens after that has the peculiarity of being embedded in a turbulent scenario. So we're describing the subsequent acceleration as the standard Fermi acceleration of magnetized clouds that you would have within a turbulent scenario. This is quantifying the same concept a little bit more in detail. For a bunch of particles ending up with different energies, there is this fast acceleration episode. This is powered by reconnection within a turbulence scenario, within a turbulence setup. Very quickly, timescale of order 10 times the Larmor time, and localized at reconnection layers. This is followed by further acceleration. Now the reconnection story is done. These particles are just scattering off turbulent fluctuations. So reconnection in this case has provided injection. The later acceleration stages are standard scattering of turbulent fluctuations on a time scale that is of order the length scale of the turbulence, where most of the power is, divided by the speed of light. How is this affected by cooling? This was also Frank's question from earlier. So we're now running in view of applying this to orphan flares, which are gamma rays inverse Compton powered flares. Same simulation, but with inverse Compton cooling losses. The critical point here is, yeah, we reproduce the hierarchy of energy scales in our simulations as expected in blazar jets. But the key point is that for blazar parameters, injection up to roughly sigma should not be affected by cooling, because the time scale for acceleration is much shorter than the cooling time. On the other hand, later acceleration phases, which proceeds on order L over C, L being the scale of the turbulence, are happening much slower than the cooling time. So fast acceleration by reconnection, not affected by cooling. Later acceleration by turbulence may be copiously and destructively affected by cooling. Why is this important? Because turbulence and reconnection within turbulence is giving rise to a very characteristic shape of the pitch angle anisotropy. So pitch angle is the angle between the particle velocity and the magnetic field. What this plot shows is that particles that are energized by reconnection, so to relatively low energy, as I said, reconnection is the first step of the acceleration, is the injection step. They are preferentially aligned with the magnetic field. Cosine alpha, alpha is the pitch angle of -1 or 1, means aligned with the magnetic field. But then scattering of turbulence leads to a pitch angle preferential such that the velocity of the particle is preferentially perpendicular to the magnetic field. So higher energy particles are in a plane perpendicular to B, low energy particles are moving roughly along the magnetic field. If you're adding cooling, as I said, the second acceleration phase is prohibited, because that will be operating on timescales much longer than the cooling time, so it means that they're actually not operating. So the only thing you're left with as an accelerator of particles is the reconnection stage, which puts particles, in the case of a strong guide field or reconnection embedded in turbulence, along magnetic field lines. Now you can see what the story is. The synchrotron emission scales with the pitch angle like sine square of alpha, and alpha now is very small. The particles are almost aligned with the magnetic field. And in fact, even though we have in our simulations magnetic energy density equal to the radiation energy density, we find that the synchrotron power is suppressed by 3 orders of magnitude with respect to the inverse Compton power. And that's exactly because of this pitch angle alignment, this velocity of alignment between the particle and the magnetic field. So the two light curves here are scaled up by a factor of 10 to the 3. So this shows that with some level of anisotropy, you don't really need extreme values. You can have efficient inverse Compton emission, but suppressed synchrotron emission. And this is typically, I would say, generically expected whenever cooling losses are preventing you to go beyond the injection stage controlled by reconnection. So with that, I will stop. This is sort of like the summary of my astrophysical implication part. Reconnection can produce non-thermal particles, potentially with hard slopes, at least below the injection break. Optical flares with polarization angle rotations, and orphan gamma ray flares. The second part, which is shorter, would have been about a new model that we have been working on with my student Navin and Andrei Beloborodov of reconnection in black hole X-ray coronae, and how this can explain the hard X-ray emission. I'm happy to take questions on that too, but I think for I think we're doing the right thing in stopping here. And Yuri will please confirm.
Okay, thanks very much, Lorenzo. This is great. Obviously, a lot of discussion already generated during the talk. But let's continue with questions. And I think the first one is Amir Levinson.
Right. So I have a comment and a question regarding your last point. So I think, let's suppose that you have a pair content. Then you need a sigma of 1,000 to produce the observations if you want to, suppress synchrotron. And then you need some form of turbulence with no guide field. For example, Sasha Philippos showed that if you have, peak simulations of kick instability, they find, low amplitude turbulence by strong guide fields with basically no acceleration.
Yes.
So this is one comment. I mean, what exactly is the setup, the global setup here?
So I think Yeah, I think it's, I would turn the question around to say, if we're requiring here moderate guide fields, which is this anisotropy, the orphan flares, I would say for a delta B over B of order 1/2, you can generate orphan flares. For delta B over B of order 1 or 2, then you could have comparable synchrotron and inverse Compton emission, which is typically what you have in blazar jets. Now, the conclusion about kink, I think I'm happy to sort of like have a deeper discussion about that, because my feeling, even at the meeting where we both were, is that they depend very sensitive to the initial conditions that are being used for setting up the equilibrium. So I'm
okay,
not.
So let's let me just follow up. Forget about the kink. In the context of your, I mean, we do see orphan flares, but most of the emission actually we don't see this. So this is like what the bulk of the emission comes from a different process, or
the bulk is I am seeing this as variations of delta B over B, and very moderate variations of delta B over B can bring to very large variations in the synchrotron to inverse Compton ratio. I can just quote a couple of numbers. The roughly equal magnitude for the two components are expected for delta B over B of 2, and delta B over B of 1/2 is what I presented with 3 orders of magnitude synchrotron below inverse Compton. So you don't need really very large variations of the delta B over B ratio for significant variations in the pitch angle anisotropy, and so the resulting inverse Compton to synchrotron ratio.
So to produce the variability, the flare duration observed, what is the special scale on which you need the turbulence to occur, roughly?
So this is sort of like in eddy scales. The time scales for the orphan flares are not extreme. So I don't think you need for that like relativistic motions or anything like that. I think something that is of order a fraction of the jet cross section will be okay here.
Evgeny Dereshev. Evgeny, you have a question?
Yes, thank you. Thank you, Lorenzo, for your talk. I have a question or maybe a comment. There is a subtlety that I do not understand. When you actually talk about radiation, not about acceleration, then it would not be possible to get efficient radiation unless you are cooling limited, more or less, or close to that. Okay, if you are cooling limited, sorry?
No, maybe we should talk about what that means. I mean, that means that the gamma cool, the cooling gamma is much lower than the energy per particle, or that you're reaching the so-called burn-off limit.
Probably the second.
Because there are very few sources in which you need particle acceleration all the way to the burn-off limit.
Wait a second. Now, if you have cooling limited acceleration, and if you accelerate at the highest possible efficiency, as probably happens with reconnection, then you actually do reach the burn-off limit. And that means the synchron radiation comes out as 100 MeV photons. But in blazars, you see synchron emission coming out as EV scale photons. This is 8 orders of magnitude less. This can be solved if you have very small pitch angles. Nice, but then you have approximately same power in synchrotron and inverse Compton. And if your pitch angle somehow is 10 to the -4, approximately equal powers of synchrotron and inverse Compton means that magnetization is something like 10 to the 8. How can this be possible? Or I'm wrong in some sense. I don't know.
Yeah, so maybe let's iterate a little bit to make sure that I'm fully following your argument, right? So So the peak of the emission in the fast cooling regime will be at the cooling Lorentz factor, right? Not at the Lorentz factor where particles are critically cooled in the sense of their cooling time balancing the acceleration time. That's if you want determining the cutoff of your particle distribution, because you cannot accelerate any particle beyond that. But I'm not sure how this will translate into the peak of the synchrotron emission. I feel I'm missing something as well. And the other point that I would make is that I don't think I'm ever invoking anisotropies that are of order 10 to the minus 4. Okay, this 10 to the 3 is alpha squared, so I need alpha of order 0.03. And that's actually a pretty extreme even case, like 3 orders of magnitude. It's definitely within the limits of not having any synchrotron flux. I think something like 0.1 for the pitch angle is already enough to explain the absence of optical flux despite the inverse Compton orphan flare. But keep going. Maybe I missed something.
I'm talking about blazars, sorry. I'm not talking about orphan flares. I'm talking about blazars where you have the synchrotron, presumably synchrotron peak at optical, and you have the inverse Compton peak, which is of comparable power, more or less, plus minus an order of magnitude. And coming to the first part of balancing acceleration and cooling, the burn-off limit is exactly balance of acceleration and cooling, provided that acceleration happens at the largest possible rate. This results in 100 MeV photons, synchrotron photons, which is absolutely not possible to reconcile with optical peak and blazar.
But I guess I'm not seeing why.
So you need a very small pitch angle.
I guess I'm not seeing why should that be determining the peak. That's the part that I'm missing. Why should the burn-off be controlling the peak and not the cooling? I see. My argument is the following. Suppose you have acceleration and switch off losses completely, then you accelerate up to something, you say this is about sigma. Lorentz factor is about sigma times mass ratio proton to electron, but that doesn't matter unless you want to make particles to radiate. If you want to make particles to radiate, you claim that they accelerate up to the cooling Lorentz factor. So and they stall at the cooling Lorentz factor. And the cooling Lorentz factor is determined by the fact that the acceleration rate is equal to the cooling rate. And if acceleration rate is charge times B times C, the largest possible, and the cooling rate is just synchronous cooling rate, this is what you get, the synchronous burn-off limit. Yes, no, I understand the physics of the burn-off. I guess what I'm missing is why are we expecting the burn-off to be the one controlling the peak? Because I can think, I mean, sure, this can be the highest energy particles that you accelerate, but why should that be controlling the peak of the synchrotron? I mean, you could have most of the particles actually not participating in the acceleration for their whole life. I mean, this is what all of the simulations show, right? They can be maximally accelerated while they're in the right region and then spending most of their time cooling after that.
This is the subtlety.
Why
this
not
is the
accelerate?
subtlety. If your cooling is much slower than acceleration, and acceleration simply doesn't provide you with particles go all the way to the burn-off limit, and this essentially means that radiation is much slower than acceleration. And if acceleration happens on the dynamical time scale, then radiation happens over much longer than dynamical time scale. That means no radiation.
Okay, maybe, maybe I'm missing something fundamental. I invite other people to jump in as well.
Okay.
Why don't you guys discuss it offline?
Okay.
Okay, Felix has the next question. Felix Aharonian. Felix. Okay, Felix disappeared. Then Paolo Buratti, do you want to ask your question?
I'm sorry. I'm just talking maybe 1 minute. Did realize that. Sorry. So I just want to say, just opposite what Evgeny said. So I like very much this pitch angle anisotropy idea, and exactly not only for the orphan flares, but also for general radiation in general. And I do understand there could be problems, but I mean, if to be a bit more general, more phenomenological. So this is a very interesting point. Evgeny was claiming that the peaks are the same level, but in fact, it's not true. I mean, the most powerful blazars, you have a Compton peak much higher, 2 orders of magnitude at least for C279. I don't know, this model is just how realistic, but it's very interesting way just to also to understand, I mean, a way to suppress radiation, synchrotron radiation. It's of course should be studied. Maybe there are principal problems, but otherwise, it's I think it's quite interesting way to suppress synchrotron radiation. And then because it's amazingly higher, this inverse Compton peak compared to synchrotron peak in powerful quasars and blazars. So just generally say I like the idea, but without details, of course, that should be discussed. So, and then Evgeny was saying that they are the same level, synchrotron, but it's not true. It's Compton peak is much higher. Well,
it's true in TVBLX, Felix.
Sorry?
It's true in TVBLX. I mean, in BLX, it's actually true.
But not the EV peak ones.
Okay, I'm just saying in general, when I see gamma ray peak is much orders of magnitude higher than synchrotron peak, I mean, it's always a bit disturbing. And so I just am claiming nothing, just saying that I like really very much this idea that there is a way to suppress synchrotron radiation.
So let me make just a couple of points on this a little bit more. So point 0, even though I presented this as a realization of reconnection in turbulence, really what you need is a comparison of the reconnecting fields with respect to the mean field not reconnecting. Okay, so then we can discuss about the bigger picture, and I think I echo very much Amir's statements of like how are we thinking about dissipation in jets, whether this is kink induced, it's a striped jet. I think I still would like to be a little bit more agnostic on that and saying it's unlikely the striped jet will produce guide field reconnection. A guide field of 10 reconnection is unlikely to be producing even marginally comparable peaks. So this is probably telling us about what are the structures within possibly kink-induced turbulence that are most relevant for the emission. The other point that I wanted to make is, so the story that I presented here was really more appropriate for flat spectrum radio quasars, external Compton, because we treat the photons as having nothing to do, the seed photons as having nothing to do with the synchrotron, other than by assuming that the magnetic energy is roughly comparable to the radiation energy in the region where the turbulence happens. And in that case, you get that the ratio of the synchrotron to inverse Compton luminosities is about alpha squared, alpha being the pitch angle in the limit of alpha much less than 1. For Emanuele, as Subaki has also worked out with me and Andrei, the equivalent prediction for synchrotron self-Compton, which will be more appropriate for BLX, for the TeV objects that Amir was mentioning and the discussion now. And in that case, the ratio is alpha. So everything else considered, I think you would expect less of a difference between the, I mean, this is oversimplifying things, okay? But in one case, external Compton, the ratio scales with alpha squared, keeping the radiation energy density equal to the magnetic energy density. For a synchrotron self-Compton, the same ratio scales with alpha, so shallower scale. And I don't want to make any further conclusion on that. I'm just stating what the role of anisotropy is for the two cases.
Okay, there is further discussion from Evgeny in the chat, so you guys can read it and discuss further offline.
Okay.
Paolo Boratti is asking, how are anti-parallel fields generated in jets?
Yeah, so I think the best scenario for having anti-parallel reconnection is a striped jet. I may have a cartoon of that. Let me check. Right here. Oh, okay, this one. So this is really a cartoon. So if you have the field in the accretion disk of a given polarity, toroidal field will be winding up one direction, accreting opposite polarity fields, oppositely directed toroidal field. And there has been now evidence, Anna Chashkina with Amir, among others, showing that different polarities can be accreted towards the black hole and launched into the jet. Whether this will indeed relax to a striped jet as we're thinking about, with one sign of the toroidal field, one sign of the toroidal field at different distances from the engine is, I think, yet to be fully determined, but that's the idea.
Okay, thank you.
Okay, and then Carl Mannheim is saying, Felix, the pitch angle anisotropy causes the M87 jet to remain dark on its axis at millimeter wavelength at 5 RG, which is light cylinder.
Yeah, I don't know.
I want to comment on that because what actually you see, even on relatively small scale, like a few hundred Schwarzschild radii, is that the jet is stratified. There is a subrelativistic sheath which accelerating. At the same time, you do see also, yeah, but I'm talking about the velocity maps actually.
Velocity maps, okay, yeah, I don't
so
have.
The velocity maps of, by Mertens from 16. And so you see most of the blobs you see are subluminal, but you see also superluminal blobs. And you don't really know what's the beaming factor also. I mean, it's, superluminal is the estimated viewing angle is limited to 5, if I remember. So I think, before we actually resolve this, it's very difficult to make any conclusion about the emission. But it's quite clear that there is some subrelativistic or malrelativistic sheath, which on these scales actually is responsible for most of the emission. So I'm not sure that it's conclusive.
Yeah, I do have, I mean, there is, I think, work that I did last year on potentially role of shear instabilities in brightening up the outskirts here, but that's for a separate talk.
Okay, are there any other questions or remarks?
I just want one quick question, Lorenzo. That you showed a plot of like magnetic turbulence in 2D. Is that what you're trying to get to with the 3D simulation? Because you were getting guide fields out of the magnetic turbulence with COMISO or something. You had a plot with multiple islands being generated self-consistently. How does that connect to? I'm also wondering where you get a realistic geometry for all the reconnection. But is that one proposal? And then if you could do a 3D simulation, you would get.
I think the fundamental link that is still to be explored is in the case there is not a striped jet, what's the geometry, the configuration, the orientation of the various reconnection regions? Because we could start with turbulence.
Yep.
And we like to think about the fact that turbulence is self-similar, independent of the way you're actually setting it up. But the reconnection layers that we are seeing and that we are mostly caring about within the turbulence simulations are actually large scale. So they are affected by the way the turbulence is realized. So whether the turbulence is generated by a kink type instability, whether it's generated by something else, whether the kink is happening at the outskirts of the jet or in the inner core, I'm expecting the properties of the turbulence and the orientations. The fact that there will be reconnection layers, I think it's relatively solid, but in terms of their properties, their geometry, their configuration with respect to the observer, I think that will not be, that will require knowing how the large scale produces the turbulence or the dissipation in a non-striped jet.
Yep. Okay.
Okay. I think we've had quite a few questions. If there are no other pressing questions, I suggest that we stop now and thank Lorenzo for an insightful, informative, and stimulating presentation.
Thank you all. And if you do have follow-up, please ask me by email, especially if I didn't properly address your questions. Let's continue this conversation by email.
Okay, thanks everyone.
Thank you, Lorenzo.
Ciao, thank you.
Thanks, Lorenzo.
Thanks, Lorenzo. Bye.
Bye.
Thanks.